Okay, so in the last video we went through and completed the first task of this example problem, which was to create a function which evaluates the Rayleigh distribution for a varied number of sigma parameter values. And in this video we'll be completing task 2, which is to create a separate function which plots the distribution function by first calling the function created in task 1. Okay, so we'll just get stuck into that now. We'll create a new file, give it a function definition at the top of the file. At the moment we won't specify any outputs. We'll give it a meaningful name. So this is to plot a distribution, so we'll call it distplot. And for the moment we won't specify any inputs. Just give it a brief description of what we know it's going to do. So it generates an annotated plot of a distribution function, and we'll go ahead and save that quickly. So once again, just reminding you that the file name of the function has to match the actual function's name, so which is distplot. So that's fine, we'll save that. Alright, so we know that this function will be calling on the first function that we created, which was the Rayleigh function. So we can already pass in, we can already give it an input. Now if we go back to the Rayleigh function quickly, we see the input function to this is sigma, which is a parameter for this particular distribution function. So later on you may want to edit this function and not plot the Rayleigh distribution function, but you may want to plot a different distribution function. So we'll pass a value into this distribution plot function and we'll call it param, which is short for parameter. Okay, and now we'll go ahead and call on the Rayleigh function as specified in the task. Okay, so we know, so we'll just give that a quick comment. So say we'll calculate the desired distribution function. Okay, so just going back to the Rayleigh function quickly, we see that it has two outputs. The first is f, which is the function values of the evaluated Rayleigh distribution, and the second is x, which is the data points used in the evaluation of this distribution. So back to our distribution plot function, let's return this f and x, these f and x outputs, but we'll call them m and n so we don't get confused as to which function out of these two that we're dealing with. So we'll let m be the function values returned from the Rayleigh function, which has the parameter input passed to it, and n will of course be the x data points used in the evaluation of this Rayleigh distribution. Okay, so passing in a varied number of parameters, just like we did in the last video for sigma, they'll be passed into the distribution plot, and then within this distribution plot function, the Rayleigh distribution will be evaluated by calling this function here. So once we have this, we can go straight ahead and plot this distribution. So just leave a comment here, say plot the distribution function for a list of varied parameter values. Okay, and so syntax for plot is as simple as this. So n was our x values that were returned from our Rayleigh function, and m holds our function values which were returned from our Rayleigh function. So that's what we'll be plotting. Okay, so we'll just save that. We'll quickly go to the command line, call this function, and see if it's operating correctly. Okay, so let's just quickly set up a varied list of parameters, and we'll call this sig again, and we'll go from 1 to 3 in increments of 0.5. So that will give us 5 different parameter inputs. Okay, so now we'll go ahead, remembering that the distribution plot doesn't return anything, so we'll just call it without assigning it to a variable. So displot, passing in the parameter inputs, which in this case is sig, and we can see we obtain plots identical to the plots obtained in the last video. Alright, so why did we create two functions? Well, I wanted to demonstrate the importance of modular programming, which is breaking a bigger problem up into its smaller tasks. So, as an example, this is our problem, and we've first created a function which evaluates a distribution, and then we created another function which plots the distribution by calling the first function. And so this is more useful than creating just one function to solve our problem. And what I mean by this is, if we just want to evaluate a Rayleigh distribution to use it for something other than a plot, then we're now able to, since we have a function that explicitly does this, which was the first that we created. And on the other hand, if we wanted to if we wanted to plot a distribution other than Rayleigh, all we have to do in our distribution plot function is change one line of code where we've called for an evaluation of the Rayleigh distribution and we'll just change this to the evaluation of whatever our desired distribution is. So that wraps it up for the example problem being solved using functions.